In this chapter, chapter 20, we're going to revisit thermodynamics to finally explain how we can identify definitively whether a reaction will happen or not all by itself. In order to assess whether a reaction happens, whether a reaction proceeds in the forward direction, the reverse direction, or occurs at all in the first place, we need to use thermodynamics. In General Chemistry 1, we visited thermodynamics for the first time and talked about heat and work. In Gen Chem 1, we defined heat, symbol Q, as thermal energy. And we said that in net, heat flows from something hot to something less hot, and that there's no true thing as cold, there's just a lack of heat. We gave signs to Q, a path function. We said that when Q is positive, that means that a system that we're interested in is obtaining heat, or heat is flowing into a system. When a system that we're interested in releases heat or loses heat, Q is negative. We defined work as a physical force to move an object a particular distance, and when a system obtains work, or when work is done on a system, the sign of W is positive. When work is released by a system, or a system does work, the sign on W is negative. Temperature is a measure of average kinetic energy, and we can measure temperature in degrees Celsius or Kelvin scales, but changes in temperature on either scale are equivalent to each other because degrees Celsius and Kelvin are just offset from each other. So delta T on both scales is the same. Enthalpy is the heat content of a system at constant pressure. The units for energy, regardless of whether we're talking about heat, work, or enthalpy, in the SI system are joules, and in the old thermodynamic workup are calories. 1 calorie is worth 4.184 joules. What's going to be new in this chapter is a discussion of spontaneity. Spontaneity, or a spontaneous chemical reaction, is a chemical reaction that occurs without any continuous outside help. Even though reactions might require a kick to get them going, a spontaneous reaction is one wherein after that kick or spark, they continue all by themselves. Think about a match being struck. Without being struck, a match doesn't spontaneously burn. But once we give that match a kick by striking it, it will burn and burn vigorously and burn until it's burnt out. So we say that a burning matchstick is a spontaneous chemical reaction. If a reaction is spontaneous in one direction, we say that it's non-spontaneous in the other, or reverse direction. When we refer to spontaneity, we are not necessarily talking about that a reaction happens instantaneously. It's just that it will happen. So we are not tying this to kinetics necessarily, and we're not timing a reaction in considering whether it's spontaneous or not. So that doesn't mean that a reaction has to be fast. We can exclusively talk about thermodynamics and kinetics separately. For example, the combustion of a matchstick is a spontaneous reaction that also happens to be fast. The reaction that causes rusting, where iron reacts with oxygen through a redox reaction to form rust, iron oxide, is a rather slow reaction. It doesn't happen right away, but it happens spontaneously. It turns out that the enthalpy for this reaction, delta H, is less than 0. It's negative 1648 kilojoules per mole. So, does that mean that all exothermic reactions are spontaneous? Certainly, the burning of a matchstick is a spontaneous chemical reaction, and it's exothermic, heat is released. So, let's talk about delta H a little bit more. When it comes to predicting spontaneity, we alluded in General Chemistry 1 that enthalpy, delta H, is a good first measure of the spontaneity for a process. The first law of thermodynamics tells us that energy is neither created nor destroyed, it just changes forms. And we generally said that exothermic processes are favorable in the eyes of the universe because an exothermic reaction is one that releases energy back to the universe. Delta H is negative for an exothermic reaction. So remember that when delta H is less than 0, a reaction is exothermic. When delta H is greater than 0, a reaction is endothermic. Consider the reaction of baking soda and vinegar. If you've seen this reaction occur, or if you go into your kitchen and make this reaction occur, you'll find that it's spontaneous. Just mix some baking soda, which is sodium bicarbonate, with vinegar, acetic acid, and you'll see an immediate vigorous response where sodium acetate is formed, as is water and a gas. We can carry out this reaction and see evidence for ourselves that this reaction is spontaneous. But if we hold the reaction vessel that we carry this reaction out in, like if you go pour some baking soda and vinegar into a glass and hold the glass at its bottom, you'll feel that the glass starts to become cold. It feels cold because energy is being input into this reaction. And our reaction has a delta H that's greater than 0. It's an endothermic process. So, even though this reaction is spontaneous by obvious evidence, delta H by itself is not sufficient to determine whether a reaction is spontaneous. In addition to simply thinking about heat energy, in order to assess the spontaneity of a reaction, we also need to think about order. What is it that drives a cup to shatter, but not to spontaneously reform into its ordered state? Why is it that when you open up your front door on a cold winter day, that heat escapes your house, but your house never warms up more than it already is? Eventually, in net, heat will flow out of your house until the temperature inside equilibrates with the temperature outside. Why doesn't your house get warmer instead of colder? Why are some processes and reactions spontaneous in one direction, but non-spontaneous in the reverse? The answer has to do with the concept of entropy. We introduced the concept of entropy earlier this semester when we talked about making solutions. In this chapter, we're going to discuss entropy further. In the reaction that we described on a previous slide between baking soda and vinegar, a reaction goes from having a solid component, sodium bicarbonate, mixing with a solution, acetic acid, to producing products that are two aqueous components, sodium cations and acetate anions, a liquid component, water, and a gas component, carbon dioxide. We've said that the universe loves to be lazy, and everything in the universe aspires to maximum laziness. And with laziness comes disorder. So not only is the universe lazy, it also loves disorder. We measure disorder by measuring entropy changes, delta S. And we say that generally speaking, disorder increases as we move from a solid to a liquid to a gas. Remember, solids are highly ordered, definite shape, definite volume structures. Liquids are a little bit more disordered, and gases are more disordered still. So the universe loves disorder, and processes that maximize disorder are favorable in the eyes of the universe. So there are two things that the universe likes. The universe craves disorder, and the universe craves maximum laziness. It doesn't want to have to do any more work than it's got to. So our universe wants two things. One, to get energy when possible. For a process to provide energy back to the universe so that our universe doesn't have to do work. And two, to make maximized disorder. If we can accomplish these two things, then the universe is satisfied with the process. We've characterized energy in terms of delta H. And in General Chemistry 1, we learned how to determine numerical values for delta H for a reaction. We came up with several different ways to get at delta H for a reaction, either through delta H's of formation, through bonds breaking and forming, or by knowing something about a chemical reaction's heat flow under constant pressure. Here, what we're going to talk about is how to measure the second aspect of things that the universe likes. How to measure the maximum disorder associated with a system. This is entropy, delta S. The universe really likes to get energy if possible. It gets energy if delta H is less than 0, an exothermic reaction. The universe spends energy if delta H is greater than 0, an endothermic reaction. So, less than 0, the universe is happy. Disorder is maximized when delta S is greater than 0. When delta S is greater than 0, we say that disorder is increasing. And in the eyes of the universe, this is favorable. Conversely, when delta S is negative, when it's less than 0, that means that disorder is decreasing, or things are becoming more ordered. Back in General Chemistry 1, we'd often draw a heating curve to show how phases change as a function of heat input. We'd draw a graph for something like water and follow the temperature of a system as heat, Q, is added to a system. At two key points, the normal freezing point and the normal boiling point for water, we see flat lines in the heating curve where we undergo phase changes for water. In the region at the bottom, we have solid in this phase change. The first flat line, solid and liquid in equilibrium. Liquid and vapor in equilibrium, and just vapor or gas beyond. What I want to focus on here is, for example, this equilibrium, the exchange between liquid and gas. And we're going to imagine compressing a gas to make it become a liquid. We're going to go down this heating curve. As we go down this heating curve, energy is expended. Delta H is less than 0 at constant pressure. We can say that heat is removed. Again, because there's no such thing as adding cold, the only way to compress a gas to a liquid is to remove heat. As we compress a gas, say in an ideal constant temperature environment, heat is going to be released from a system in order for liquid to form. So if we look at this animation up above, as we compress and move this piston downward, we liquefy any gas particles that are in there. And we move from having any old particles in there that are gaseous into having those gaseous particles condense into the liquid phase. This is a reversible process because we could imagine going back up this staircase again, in which case delta H is positive and Q is added. It takes the same amount of heat energy in a constant temperature bath to go this way along this flat line between liquid and gas as it takes to go in the opposite direction from right to left. That means that any Q that's added, heat energy that's added for this process, is equal to any heat energy that's expended by this process. Because these are the same thing, we can call this a reversible heat energy. We call it Q reversible, or just QREV for short. Because the phase change between liquid and gas occurs at a constant temperature, we can relate the amount of heat energy that's either being input to vaporize our liquid or being removed to condense our gas relative to the temperature at which this occurs, like 100 degrees for water. And with these two concepts in mind, really the only thing that we are changing about our system in this flat line region is the amount of order or disorder associated with our system. So as heat is expended at this constant temperature or heat is added at this constant temperature, the major aspect of this system that is changing is the amount of disorder on a microscopic scale of, say, water molecules in their liquid or gaseous form. We call that disorder entropy. Disorder changes as heat is exchanged at constant temperature. Right along this flat line in the phase change diagram for water. Disorder is measured by entropy, delta S. So this whole thing is disorder, delta S. And that is equal to the amount of heat that's exchanged, this reversible Q, divided by temperature. For a constant temperature process, the entropy of a process, or a change in order of a process, is given as heat exchanged, reversible Q, divided by temperature. Therefore, units of delta S, units of entropy, will be joules per Kelvin or joules per mole per Kelvin. Generally, what we can say is that entropy increases the further up this heating curve we go. Solids are more ordered than liquids, which are more ordered than gases. And so in the eyes of the universe, it's more favorable to have a gas than it is to have a liquid, than it is to have a solid. And in some circumstances, this favorability in disorder, maximizing disorder, can overcome or compensate even an endothermic process's lack of energy given off to the universe. So I know now you're thinking that water freezes spontaneously when it's cold out. We've all seen a pond or lake freeze up when the temperature drops below the freezing point outside. That's not an increase in disorder. That's an increase in order. The change in entropy isn't positive. It's not greater than zero then, because things are becoming more ordered when water freezes. So that must violate everything I just said, right? Well, not entirely. Because when we think about order versus disorder, what we really have to consider is the order and disorder in the universe as a whole. And we have to come up with a second law of thermodynamics. Remember, the first one is that energy isn't created or destroyed. There are lots of different ways to say the same thing about the second law of thermodynamics. But the way that I'll introduce it to you here is one in which we can tie together the concepts from the previous slide with this one. The second law of thermodynamics tells us that a spontaneous process is one that increases the overall entropy of the universe, even if that means that either the system that we're interested in increases in order, or the surroundings around that system increase in order, meaning that their entropies decrease. We have to consider three things: the entropy of the universe versus the entropy of a system that we're interested in versus the entropy of the surroundings for that system. The second law of thermodynamics focuses only on the entropy of the universe and whether the universe as a whole is satisfied with changing. When water freezes spontaneously when it's cold outside, it turns out that the entropy of the universe is satisfied with that change. And we're going to explain why in just a few moments. Before we do so, let's review these terms: system, surroundings, and universe. A system is a component of the universe that we're interested in. Maybe it's a chemical reaction or a body of water. Everything that's not the system, all of the rest of the universe, are the surroundings for that system. So that together, the system and surroundings make up the entirety of the universe. So the system's the only little facet of the universe that we care about for a moment in time. Surroundings are everything else, and together those two components make up the universe. So what happens then when water freezes? Let's one more time look at the heating curve for water. And this time, I'd like for us to focus on this solid liquid line. What we're saying is that it's spontaneous for water to freeze, to go from liquid to solid when it's cold outside. So let's pick a temperature, any temperature. Say negative 10 degrees Celsius. When it's negative 10 degrees Celsius outside, we expect water will freeze. And it will do so spontaneously. Does that mean that the surroundings of our water, or our water itself, have changed their disorder at all? Well, certainly what we can say about the water itself, if water is our system, the thing that we're interested in. Our water has gone from being liquid to solid, so it has become more ordered. Or another way to think about that, less disordered. Mathematically, the entropy of our system has changed so that it is now less than zero. But what about our surroundings? Our surroundings are everything else in the universe that's not the water at negative 10 degrees Celsius. So what are those surroundings? And how does their disorder change? So everything that's not water, everywhere in the universe, are surroundings. How do we calculate how much our surroundings have changed? Well, we just came up with an equation on the previous slide to do so. We said that the change in entropy, delta S, for a process is given by Q for that process divided by temperature. In the process that we're thinking about here, where water is freezing, we're at a constant temperature as we move through a phase change where liquid goes to solid, that's 273 K. So we know that the temperature that water freezes at is 273 K. And we also know something from earlier this semester about a phase change. Earlier this semester, we said that this phase change is associated with a quantity called the enthalpy or heat of fusion, the delta H of fusion. And this has a tabulated numerical value for water. For water, that's 6 kilojoules per mole. So, is that 6 kilojoules per mole worth of energy being given to or taken away from surroundings? In other words, is this 6 kilojoules per mole number a positive value or a negative value for everything that's not water, but in the surroundings instead? Well, as we move down this graph, we said that delta H is removed. Delta H is less than 0 for our water, the system that we're interested in. But as that energy is removed, where does it go? Well, it goes to anywhere that's not water. And we said that anywhere that's not water are surroundings. So our surroundings must be acquiring any heat that our water is giving off as it solidifies. Because once again, according to the first law of thermodynamics, heat can't be created or destroyed. So any heat that's lost from this water as it freezes can't just disappear into the ether. It's got to go into the surroundings. So from the perspective of the surroundings is obtaining heat energy. It's getting positive 6 kilojoules per mole as water is freezing at this temperature, 273 Kelvin. It really doesn't matter what these numerical values are, but what we can say is that the change in entropy for our surroundings is much, much greater than 0. It's a really big number. So even though our system, water, is becoming less disordered, it's got an entropy that's negative. The surroundings of that water are becoming much, much more disordered. The entropy of surroundings is much, much greater than 0 because heat energy is being given off from water to its surroundings. Together then, because these two quantities, the entropy of a system and the entropy of surroundings, make up the universe as a whole changes its entropy in a positive way. Together, the change in entropy for our system, which is negative but small, plus the change in entropy for the surroundings of that system, which is positive and big, equal the change in entropy for the universe as a whole. In total, because this is a small negative number and this is a big positive number, the entropy of the universe is positive. And from the perspective of the universe, this is great. Notice what happens, though, as we increase the temperature above 273. As we get hotter and hotter, as temperature rises above 273, this whole number gets smaller. This gets small. And eventually, it gets too small to compete with this, anywhere over 273. And this number can no longer outweigh this one, so that the entropy change of the universe would no longer be positive at temperatures higher than 273. Starting at 273 K, 0 degrees Celsius, water can freeze because at that point we reach a tipping between how the entropy of the surroundings outweighs the entropy of our system. And this is where we should hear trumpets, because this is the second law of thermodynamics. Any process where the overall entropy of the universe is positive, is a spontaneous process. For a molecular level view of what entropy really is, I'd encourage you to watch this linked YouTube video. I have a link to it both in your PowerPoint slides on your Moodle page, and I've added a link in the video description below. So check that out. Entropy itself, all by itself, has some meaning. Not just changes in entropy, but also a 0-point entropy. Therefore, we can think about the entropy and not a change in entropy for a substance. We can use these so-called absolute entropies to compare directly one substance at one set of conditions to another substance at either the same or a different set of conditions. So unlike enthalpy, there's a 0 point for entropy. We could think about an ideal case where there is perfect order. There's no disorder at all. We'd say that this ideal case occurs at absolute 0, the coldest possible temperature it could be, in a perfect crystal, a crystal that has no defects, where everything is highly ordered. In a perfect crystal at absolute 0, there is perfect order. And we say that the entropy of a so-called perfect crystal at this hypothetical set of conditions is 0. This sets the 0-point entropy and forms a basis for measuring the entropy of everything else relative to that point. So this is S all by itself, rather than just delta S. So not only do changes in entropy, delta S, have meaning, but so too do absolute entropies, just S for a substance. An absolute entropy will tell us how much more disordered a given system is at a certain set of conditions compared to another set of conditions or to another substance. This is the third law of thermodynamics. The third law states that a perfect crystal at absolute 0 has 0 entropy. Because we can set a baseline for comparison of entropies, absolute entropies of substances, we can come up with a way to compare and contrast substances as a function of these absolute entropies. As a means of comparison, we'll compare the same amounts of stuff, and we'll compare on the basis of mole quantities. So our amount of stuff will be 1 mole, and we'll compare at a given temperature, like room temperature, 298 K. This is a standard molar entropy, and we get this little naught symbol to indicate standard conditions. So standard conditions identified by a naught sign, just like in General Chemistry 1. Standard molar entropies, S naught, will have units of joules per mole per Kelvin, and will be given for specific conditions of standard temperature for 1 mole worth of stuff. And what's more, we can come up with a list of factors that affect entropies, either standard molar entropies or entropies in general. For one thing, temperature affects the absolute entropy for a substance. Regardless of the substance that we're interested in, we'll say that as temperature increases, as T goes up, the absolute entropy for a substance goes up. Why is this? Well, as we increase temperature, we increase the average kinetic energy, or on a microscopic scale, the amount of average energy that a particle has. Remember that the average kinetic energy can be given as 3/2 times kb times T, where kb is a Boltzmann constant for a molecule. As temperature increases, as T goes up, because Boltzmann constant is constant, the average kinetic energy of particles increases. As that average kinetic energy increases, things are more chaotic and therefore more disordered. So as Ke increases, more disorder ensues. So as temperature increases, disorder increases, and the absolute entropy for a substance increases. For a second related factor, we'll think about the physical state of a substance. Typically, we can associate changing physical state with changing temperature. And as we do so, as we change a physical state from, say, solid to liquid to gas, our entropy changes concomitantly. So going from solid to liquid to gas results in increasing entropy. We've already discussed this. We've said that a liquid is more disordered than a solid, and a gas is more disordered than a liquid. So we should expect that as we change these physical states, for the entropy to increase in association. There are a few caveats to this concept. Generally speaking, by making a solution an aqueous phase, that aqueous phase usually has more entropy than a solid and a liquid alone. So generally, adding a solid to water to create the aqueous phase for that solid results in an increase in entropy, with an exception being if adding a solid to water to make an aqueous phase increases the order of water. If it creates water molecules ordered so highly around individual ions or particles that water's order is increased. In certain exceptions, when water becomes more ordered, by adding a solute. In addition, we can say that covalent solutes have less entropy overall than ionic soluble salts, because covalent compounds don't split up into component ions and therefore remain just as ordered themselves intramolecularly in solution as outside of it. So they don't have as large an entropy as soluble ionic salts. Again, because covalent compounds have no ions to split into. Lastly, gases increase in order when they're solutes. Gases by themselves already have high entropy, so trying to force a gas into an aqueous phase actually decreases the entropy of a gas. Its entropy goes down when they're forced to be solutes in aqueous phase. And the last factor or set of factors that affect entropy are general atomic or molecular characteristics. We're going to say a little bit about what we mean here, but there are a wide variety of factors affecting the characteristics of an atom's or molecule's entropy. What we can generally say is that for atoms, increasing atomic number means increased entropy. So that heavier and heavier atoms increase entropy. This is because for heavier and heavier atoms, we're increasing the amount of occupied energy levels that electrons can occupy, that nuclei can occupy. For molecules, we have to think about two competing factors. Molecules have mass considerations as well as shape. In General Chemistry 1, we described how to visualize or represent the three-dimensional shape of a molecule. We have to think about both of these things simultaneously in order to assess the entropy of a molecule. But what we can say universally is that both of these considerations give rise to a descriptor called the molecular degrees of freedom of a molecule. Entropy for a molecule depends on how many degrees of freedom that molecule has. Degrees of freedom, or DOF for short. We won't belabor this idea, but we do need to explore it to some extent. This concept of degrees of freedom refers to all the ways in which a molecule can spread out or disorder all of the things that it does. The types of things that a molecule can do: molecules can move through space. This is called translation, moving from one place to another. So a molecule moves from here over here. It has translated. Molecules, because they are created from bonds, have vibrations. So molecules can vibrate bonds. And molecules' bonds can rotate. If we think about a simple molecule like H2 and think about H's being connected on a spring, those two hydrogen atoms can vibrate. They can move back and forth in their bond, away from each other or towards each other. And simultaneously, they can rotate around their bond while vibrating. Also, this H2 molecule can move from one place to another. It can translate. So it can move in a straight line direction, up and down, left and right, all while vibrating and rotating. So there are multiple different ways in which the degrees of freedom can be distributed for a molecule. Generally speaking, the more degrees of freedom, or ways that we can distribute these motions, the greater the entropy for a molecule. And we can summarize that by saying that as molar mass increases, as molar mass goes up, the number of degrees of freedom go up. So the entropy of a molecule goes up. So the heavier a molecule, the more degrees of freedom it has, and therefore the more entropy it can have. For example, nitrogen dioxide has a higher entropy, a greater standard molar entropy than nitrogen monoxide, NO. Numbers of degrees of freedom are increased when restrictions are removed. So when crystallinity or order decreases, increase the number of degrees of freedom. And so increase entropy. An example of this is in the allotropes of carbon. Allotropes are different forms of the same phase of material. Carbon as a solid exists in several different forms. One form is graphite, graphitic carbon. Another form is diamond. The diamond form of carbon is far more ordered and crystalline than the graphitic form of carbon. And we say that because of the difference in order, there are more degrees of freedom associated with graphite than there are with diamond. Graphite is more free to move around and become disordered than diamond is. So the standard molar entropy of graphite is greater than the standard molar entropy of a diamond. One additional way to think about this concept, example number 2 of this order change, is comparing isomers of the same molecular formula. Isomers are things that have the same chemical formula, but different structures or connections between atoms. So we're going to look at isomers specifically of a molecule with a chemical formula C5H10. There are two different ways that we could think about drawing the Lewis structure for C5H10. One way might be in this method. We draw a double bond between two carbons and single bonds to all the rest. Every carbon gets a total of 4 bonds, and each one of those bonds that isn't attached to a carbon gets as many hydrogens as can be accommodated. Here there are 1, 2, 3, 4, 5 carbons, 1, 2, 4, 5, 6, 7, 8, 9, 10 hydrogens, C5H10. Another way that we can draw this same chemical formula is to think about carbons in a loop. So maybe I draw these carbons in such a way that 5 are connected together in what looks like a pentagon. Each one of these carbons again gets 4 bonds, so each one will have a connection to as many hydrogens as can be accommodated to make the number of bonds total equal to 4. Here again we have 5 carbons and 2, 4, 6, 8, 10 hydrogens. Both of these drawings represent C5H10. So, are they both the same standard molar entropy? They're not. And the reason that they're not the same standard molar entropy is that this version of the molecule down below in blue is far more restricted in its motion because it's locked together in this cyclical shape compared to the molecule up above drawn in black that's spread out. A lack of restriction in the molecule up above, because there's less restriction, there's more opportunity or more freedom to move about. So the standard molar entropy for this isomer of C5H10 is higher or greater than the standard molar entropy of the cyclic C5H10 molecule. We can use this concept of standard molar entropy and tabulated values of which to do things like calculate the overall entropy change for a reaction. Back in General Chemistry 1, we came up with an equation that allowed us to calculate the overall enthalpy change for a reaction, given that we knew something about the sums of all of the enthalpies of formations of all of our products, multiplied by numbers of moles, and could subtract from that the sum of all of the standard enthalpies of formation of our reactants, multiplied by numbers of moles, n. We can do something similar with entropies. If we know the standard entropy or the standard molar entropy for all of our products and all of our reactants, we can calculate a standard entropy change. The standard entropy change, delta S naught, is given as the sum of the number of moles of all of our products, each respectively multiplied by the standard molar entropy of our products. And we subtract from this quantity the sum of the numbers of moles of each of our reactants multiplied by the standard molar entropy of each of our reactants. For example, if we know the standard molar entropy for everything in this reaction between ammonia and oxygen to make nitrogen monoxide and water vapor, then we can calculate an overall entropy change at standard conditions for this reaction. For our products, we know that we can calculate this quantity here by taking our coefficient of every product in turn, multiplying by the respective standard molar entropy, and summing these results together. For NO, our coefficient is 4, and our standard molar entropy is given as 211 joules per mole per Kelvin. For H2O, our coefficient is 6, and our standard molar entropy is given as 189. In total then, the sum of all of our products' standard molar entropies is equal to 4 times 211 plus 6 times 189. We can do something similar for all of our reactants, calculating the second term in our equation up above. For ammonia, NH3, we have a coefficient of 4 and a standard molar entropy of 193 joules per mole Kelvin. And for oxygen, even though it's in its elemental form in its standard state, we still have a standard molar entropy, because unlike enthalpies of formation, standard molar entropies do have a 0 point at absolute zero. This is not a reaction that happens at absolute zero for a perfect crystal, so according to the third law of thermodynamics, even elements in their standard state still get a standard molar entropy that's non-zero. For oxygen, that's given as 205 joules per mole K. In total then, the sum of all of our numbers of moles of reactants multiplied by their respective standard molar entropies is equal to 1797. Taking the difference between this term and this term gives our overall entropy change, delta S, for our reaction. 1978 minus 1797 is equal to 181 joules per mole per Kelvin for our reaction. So, is this a reasonable result for this reaction? Well, if we look at the reactant side of this reaction, what we'll see is that both reactants are gaseous. There are 4 moles of ammonia and 5 moles of oxygen. In total, there are 9 moles of gas on the reactant side. On the product side, we form 2 gaseous materials, nitrogen monoxide and water vapor. There are 4 moles of NO, 6 moles of H2O. There are 10 moles of gas on the product side. We go from having 9 moles of gas to having now 10 moles of gas. We've made more gas. And therefore, we should expect that we increase the disorder associated with our system. If there's more gas, there's more opportunity for disorder. Therefore, we should expect the change in entropy to be positive. A positive change in entropy means more disorder. So this is commensurate with what our expectation would be, an increase in entropy as this reaction occurs. But that result doesn't necessarily determine whether the reaction that we just looked at is spontaneous. In order to evaluate whether a reaction is spontaneous, we need to know something about the total entropy change of the universe. We need some means by which to calculate a change in entropy of surroundings, in addition to just our system. In the reaction that we looked at in the previous slide, our system was our reaction of ammonia and oxygen. And sure, for that system, entropy increased. But we don't know yet whether the entropy of the universe is increased by that reaction happening. In order to evaluate the entropy change for the universe, we need the change in entropy for both our system and our surroundings. And we're going to try to arrive at an estimation of the change in entropy of surroundings just by knowing something about the reaction or system itself. We know that exothermic reactions release heat to surroundings. If that's the case, then molecules in surroundings, once receiving heat, can increase their average kinetic energy and gain more freedom of motion, so achieve a higher entropy. Whereas endothermic reactions steal heat from surroundings and thus restrict freedom or decrease disorder and therefore entropy in the surroundings. The temperature at which we carry out a reaction is also influential. At very low temperatures, like as we approach absolute zero, a contribution of heat from an exothermic reaction or a removal of heat via an endothermic reaction from surroundings is a big deal because surroundings don't have that much heat to begin with if they're at low temperature. But at high temperature, there's an excess of energy in surroundings. So it's not as big a deal to lose some or gain some more just from a small little reaction happening. It's like if you had a whole lot of money, you wouldn't really care about giving away a penny. But maybe if you're penny pinching and don't have very much to begin with, a penny means a lot to you. It's the same for temperatures. So let's think about this reaction, the reaction of ammonia and oxygen occurring at room temperature, 298 K. We're going to calculate the entropy of surroundings, knowing something about the enthalpy of this reaction. So, this is General Chemistry 1 thermo. We're given here delta H's of formation, enthalpies of formation of all of our products and our reactants. We're going to calculate first an enthalpy change for the reaction as a whole. And then we're going to use the second law of thermodynamics to help us see if this reaction is spontaneous. Remember that the enthalpy of a substance can be calculated in its change as reversible Q divided by a constant temperature, T. In this scenario, our reaction itself is the system, and everything that's not this reaction are surroundings. If our reaction is exothermic, that means that our surroundings receive energy from our system. If our reaction is endothermic, then that means that our surroundings give up energy to our system. So another way to say this is that the entropy of our surroundings is dictated by the enthalpy of our reaction. And whatever the sign on our enthalpy for a reaction is, the sign associated with surroundings is going to be opposite, negative. So delta S of surroundings is like the negative enthalpy of our reaction, because whatever our reaction does, the surroundings respond with an opposite sign. An exothermic reaction means that our surroundings get heat energy. Negative of a negative is positive. An endothermic reaction means that our surroundings give up energy. Negative of a positive is negative. Therefore, in order to give a numerical value to the change in entropy of our surroundings, we're going to need to calculate the enthalpy of our reaction. So we're going to do that under standard conditions. The change in enthalpy for our reaction, again, can be given as the sum of the number of moles of products multiplied by their respective delta H's of formation, subtracting the sum of the numbers of moles of reactants multiplied by their respective standard enthalpies of formation. So what that ultimately looks like, again, as a review from General Chemistry 1, is this. For each of our products in turn, we'll take our coefficient, multiply by the tabulated value of enthalpy of formation given here. For NO, we have a coefficient of 4 and a given enthalpy of formation of 90.3 kilojoules per mole. For our other product, water, we have a coefficient of 6 and an enthalpy of formation of negative 241.8. That suffices for all of our products. For our reactants, we have a coefficient of ammonia of 4 and an enthalpy of formation of negative 46.1. Because oxygen is an element in its standard state, there is no enthalpy of formation because it wouldn't make sense to come up with a chemical reaction that forms O2. It's already an element in its standard state. So, when we calculate the enthalpy change for this reaction, delta H for our reaction we'll find is equal to negative 905 kilojoules per mole of reaction. We can use this information to solve for the change in entropy of our surroundings. If we know that the change in entropy of our surroundings is negative, whatever the delta H for our reaction were, divided by the temperature that this reaction occurs at, then the delta S of our surroundings under these standard conditions is given as negative delta H, which itself is negative 905 kilojoules per mole, divided by temperature, which we're told is 298 K. This means that the change in entropy for our surroundings is positive 3.04 kilojoules per mole per Kelvin. Now, if you remember, on a previous example, we calculated this change in standard entropy for our system in joules per mole Kelvin. So let's convert this quickly to joules per mole Kelvin to be consistent with the units that we used before. Multiply by 1,000, 3,040 joules per mole K. Earlier, we'd calculated that the change in entropy under standard conditions for the system, our reaction, was positive 181 joules per mole Kelvin. So sure enough, it looks like both the change in entropy for our system, the reaction itself, and the surroundings of that reaction are both positive. If we add these two things together, according to the second law of thermodynamics, then the change in entropy for the universe as a whole is equal to the change in entropy for surroundings, 3040, plus the change in entropy for our system, 181. In total, a positive change in entropy for the universe. According to this result and the second law of thermodynamics, the universe is happy with this end result. We say, since the change in entropy for the universe for this reaction is greater than zero, the second law of thermodynamics tells us that this reaction is spontaneous. It will happen all by itself without the need for any outside intervention. This is the culmination of our discussion on spontaneity. According to the second law of thermodynamics, when the change in entropy for the universe is positive, then a reaction or process is spontaneous. That seems like a lot of work to go through just to figure out whether a reaction is spontaneous or not. So, because it's tedious to measure the entropy of every system that we're interested in and the surroundings of every system that we could ever come up with, there is another way that we can approach this problem of predicting spontaneity at constant pressure. At constant pressure, for constant pressure processes, like things that we do in open air laboratories, we can derive the following shortcut to predict spontaneity. We know from the second law of thermodynamics that the change in entropy of the universe is given as the change in entropy for a system that we're interested in, plus the change in entropy for the surroundings of that system. And what's more is that on the previous slide, we saw that the change in entropy for surroundings of a chemical reaction was equal to negative whatever delta H for that reaction, or our system were, divided by temperature. This means that we can plug in this expression wherever we see delta S of surroundings above. So the change in entropy of the universe is equal to change in systems or reactions entropy minus delta H of our system divided by temperature. If we multiply through everything by T and take a negative along with it, we multiply every single term by negative T to keep our equation consistent. What we end up with is, on the left-hand side, negative T delta S for the universe. On the right-hand side, negative T delta S for our system or our reaction, plus delta H for our system or reaction. I'm going to rearrange this just a little bit. I'm going to say that the right-hand side is delta H for our reaction minus T delta S for our reaction. And on the left-hand side, I'm going to give this entire term, negative T delta S, a new name. This has a special connotation in thermodynamics. This is called the Gibbs energy of a system. And we're going to call the Gibbs energy delta G. This is perhaps the most important equation that we'll come up with in this chapter. You should try to memorize this equation because we will see it over and over again. According to this equation, the change in Gibbs energy for a reaction at constant pressure is equal to the change in enthalpy for that reaction minus T delta S for that reaction. The Gibbs energy change directly gives us an indicator of the spontaneity of reaction. So this is an incredibly important concept. Delta G for a reaction when less than 0 means that this whole quantity, negative T delta S, is less than 0. And a negative of a negative means that delta S must be positive. What this ultimately means is that any time delta G for a reaction is less than 0, a reaction is spontaneous. So anytime delta G is negative for a reaction, we have direct, incontrovertible evidence that a reaction is spontaneous. And conversely, if delta G for a reaction or process is positive, if it's greater than 0, then a reaction or process is non-spontaneous. And with this measure of spontaneity, the Gibbs energy, or delta G for a reaction or process, we can directly predict the spontaneity of a chemical reaction. So with that, let's take a more direct route towards determining the spontaneity of the reaction of ammonia and oxygen without having to calculate the entropy of the surroundings. We should be able to directly identify whether this reaction is spontaneous on the basis of calculating a Gibbs energy for the reaction. According to our previous results, our enthalpy of reaction, delta H, is negative 905 kilojoules per mole. And our entropy of reaction is 181 joules per mole per Kelvin. In order to keep energy units consistent, perhaps we can convert this to kilojoules per mole per Kelvin. When we calculate the Gibbs energy change for this reaction under these standard conditions, and therefore we'll give a naught symbol for a standard Gibbs energy, we'll come up with delta H, negative 905 kilojoules per mole, minus T, the 298K, delta S, 0.181 kilojoules per mole per Kelvin. Calculating the result, we get delta G for this reaction is negative 959 kilojoules per mole. And the result of this directly informs whether this reaction is spontaneous. Here we say that because delta G is less than 0, since delta G of our reaction is less than 0, our reaction is spontaneous. Without having to go through the slog of math that we did on a previous slide, we can tell directly from this calculation whether a reaction is spontaneous or not. So, this Gibbs energy change tells us something about the spontaneity of a process. Again, if the change in Gibbs energy is negative, less than 0, a reaction is said to be spontaneous. And if the Gibbs energy change is positive, then that reaction is non-spontaneous. We can use the signs of enthalpy and entropy to predict the spontaneity of a reaction. According to the equation that we just derived for our Gibbs energy, the Gibbs energy change for a reaction is equal to delta H for a reaction minus T delta S for that reaction. If delta H is negative for an exothermic reaction, and delta S is positive, then a negative number minus a positive number will always result in a negative result, meaning that delta G will always be negative anytime delta H is negative and delta S is positive. Therefore, a reaction that has an exothermic delta H and a positive delta S will always be spontaneous. An endothermic reaction, one in which delta H is positive and has a negative delta S, meaning that entropy is decreased, can never be spontaneous. This is because a positive number minus a negative number can only ever be positive. An endothermic reaction, one where delta H is positive, can be spontaneous only if delta S is positive and the temperature is high. A positive number minus a positive number is only negative when this term on the right-hand side is big. At high temperature, an endothermic reaction is spontaneous at high temperature, if and only if our entropy is positive. An exothermic reaction can be spontaneous at low temperature, even if entropy is negative. If a reaction results in a decrease in entropy, a release of energy from an exothermic process is required. But temperature has to be low in order to accomplish this, so that the surroundings maximize their energy increase. A negative number minus a negative number is only negative still if this right-hand term is small. And we can predict when a reaction goes from being spontaneous to non-spontaneous. A reaction can change from being spontaneous to non-spontaneous at a particular temperature. In order to evaluate when a reaction goes from spontaneous to non-spontaneous, we have to evaluate what happens as delta G goes through zero, or in other words, when zero is equal to delta H minus T delta S for a reaction, the tipping point for changing the spontaneity of a reaction. Taking the term T delta S over to one side, we get this result. And dividing through by entropy, we arrive at this relationship. The tipping point for any reaction moving from spontaneous to non-spontaneous can always be given by a Kelvin temperature. That's the ratio of the enthalpy for a reaction to the entropy of our reaction. Notice that a reaction that's always spontaneous at any temperature would result in a Kelvin temperature that's negative, which is an impossible result. A reaction that is never spontaneous at any temperature also results in a negative T, which is a physically unrealistic result. So I said a few weeks ago that what we were ultimately after in thinking about equilibrium in thermodynamics was to predict the spontaneity or degree to which a reaction proceeds to products or reverts to reactants. Now that we know some means by which to calculate the spontaneity of a reaction through Gibbs energy, we can start to relate that idea to equilibrium. Under standard conditions where we have concentrations of solutions equal to 1 mole or partial pressures of gases equal to 1 atmosphere and every substance in a standard state, we can relate directly the equilibrium constant for a reaction to the change in Gibbs energy for that reaction through this equation. Delta G is equal to negative RT times the ln of K. In this equation, delta G naught is our standard Gibbs energy for a reaction. R is the ideal gas constant given with a value of joules per mole per Kelvin, or kilojoules per mole per Kelvin. T is therefore our Kelvin temp, and K is our reaction equilibrium constant. In this equation, notice that if K is greater than 1, meaning it's a big number, then the natural log of a big number is a positive value. And multiplying a positive value by negative RT gives us a negative Gibbs energy. So when K is greater than 1, we say that a reaction is spontaneous in the forward direction. When K is less than 1, the natural log of that small number is negative. Negative of a negative is positive, and the standard Gibbs energy switches to positive value, suggesting that a reaction is non-spontaneous in the forward direction. Let us now use this concept to calculate an equilibrium constant directly from thermodynamic data for a reaction that's reached equilibrium. At equilibrium, for a reaction shown here between dinitrogen tetroxide and nitrogen dioxide, the standard Gibbs energy change for the reaction is given as 4.8 kilojoules per mole. We're going to calculate K for the reaction, and then we'll come to these other 2 bullet points. So, firstly, our equilibrium constant, K. We can determine from the reaction up above, given the equation that we've just investigated. Delta G for this reaction is 4.8 kilojoules per mole. Therefore, we're going to need an ideal gas constant with matching units. I'm going to choose to use 8.3145 times 10 to the minus 3 kilojoules per mole per Kelvin. We're told that this reaction occurs at 298 K. So we're going to solve for our equilibrium constant, K. The first thing that we'll need to do is divide both sides by negative 8.3145 times 10 to the minus 3 times 298. So I will take this whole quantity over to the left-hand side. Notice that all units on the left will cancel out, and when we plug all of that stuff into a calculator, we end up with negative 1.94 on this left-hand side. That's equal to the natural log of our equilibrium constant K. To undo a natural log, raise e to the power of both sides. That undoes our log, and K is just e to the negative 1.94. Type that into our calculator, and we end up with 0.14. 1.4 times 10 to the minus 1 power. That's our equilibrium constant for this reaction under these conditions. So K is 0.14, less than 1, like we might expect, given that the Gibbs energy change for this reaction is positive. Now the next thing that we're asked to do is to find a Gibbs energy change under non-standard conditions at a temperature of 298 K, but where the concentration of NO2 is 0.02 molar, and the concentration of N2O4 is 0.005 molar. So we're going to need to think about the relationship between delta G under standard conditions, the equilibrium for a reaction, and delta G under non-standard conditions. I'm going to get rid of our work down below, and then we'll come up with an equation to satisfy this relationship. So the equation that I showed you here applies to delta G under standard conditions. The conditions outlined on the slide above. But what happens under non-standard conditions? Under non-standard conditions, we have to consider the concentrations of our reactants and products and their relationship to each other. Non-standard Gibbs energy, just delta G, no not symbol like up here, can be related to delta G under standard conditions. Delta G under non-standard conditions is equal to delta G under standard conditions offset by some value, specifically offset by RT times the natural log of not K, but Q. This is our old friend, the reaction quotient, Q. So Q is our reaction quotient. It's written in exactly the same way that K is written, except it just provides a snapshot of a reaction that may or may not be at equilibrium right now. So we can think about non-standard conditions for Gibbs energy as being analogous to a reaction that's not at equilibrium. In this example, we can calculate a reaction quotient Q by taking the concentration of our product, NO2, squaring it, dividing by the concentration of N2O4, our reactant. We know the concentration of our product is 0.02 molar. And the concentration of our reactant is 0.005 molar under these non-standard conditions. So our reaction quotient is 0.080. Sure enough, our reaction is not at equilibrium because Q is less than K. Which direction, according to Le Chatelier's principle, will our reaction proceed in order to establish equilibrium? Because Q is small compared to our known value for K, will our reaction make more products or will it make more reactants? Good. Our reaction will make more products. You answered correctly in my mind. Because this Q is small, that means that there aren't enough products yet. So this reaction is going to have to proceed from this point onward towards making more products. Let's see if that gets reflected in our non-standard Gibbs energy. We should expect that it should be spontaneous from here on out to make more products until our reaction establishes equilibrium. Delta G is equal to our standard Gibbs energy, which we were given as 4.8 kilojoules per mole, plus RT, I'll use again R in kilojoules per mole per Kelvin. T is still 298 K times the natural log of our reaction quotient Q, which we have just calculated as 0.080. If we plug all of this into a calculator, what we get is that this non-standard Gibbs energy is equal to negative 1.5 kilojoules per mole. Sure enough, under these non-standard conditions, our non-standard Gibbs energy under these conditions is negative. Since delta G under these non-standard conditions is negative, our reaction is spontaneous in the forward direction, in the direction that makes products. This is an expected result based upon Le Chatelier's principle. We knew that because Q were small compared to K, that our reaction was going to have to produce more products in order to reach equilibrium. Thermodynamics verifies this for us. It tells us that under these conditions right now, our reaction's Gibbs energy is negative and therefore our reaction must proceed in the forward direction toward making products spontaneously, and that's what it will do in order to establish equilibrium. So what happens when this reaction ultimately does reestablish equilibrium to this non-standard Gibbs energy, this just delta G without a naught symbol? What value will this delta G take on when our reaction has once again reached equilibrium and Q has become equal to K? So, when our reaction reaches equilibrium again, we can calculate the non-standard Gibbs energy through the standard Gibbs energy plus RT ln of Q. And we know a few things. We know that at equilibrium, the value for Q will exactly match the value for our equilibrium constant K. So delta G would be equal to our standard Gibbs energy plus RT times the ln of K, because K is the same thing as Q at equilibrium. Earlier on, we showed that delta G under standard conditions is the same as negative RT times the ln of K. So if we substitute that in, delta G under non-standard conditions is negative RT ln of K plus RT ln of K. These two things cancel out, and our non-standard Gibbs energy goes to 0. All right, one last equation that applies to Gibbs energies. And in this vein, we can talk about Gibbs energies in precisely the same way that we talked about enthalpies in terms of formation. Just like we assign enthalpies of formation and standard molar entropies for individual substances, we also define Gibbs energies of formation, or delta G of formation. This tells us about the spontaneity with which a particular compound is formed from its respective elements. The Gibbs energy of formation, or delta G of formation, can be used in turn to calculate the overall Gibbs energy change for a reaction. So delta G for a reaction under standard conditions can be given as the sum of all of the numbers of moles of products times the standard Gibbs energy of formation of product minus the sum of all of the numbers of moles of reactants in turn multiplied by their respective Gibbs energy of formation. Very similar to the two equations that we derived earlier for both the enthalpy of reaction and the entropy of reaction. If we know tabulated values of the Gibbs energy of formation of products and reactants, we can calculate the overall Gibbs energy change for a reaction. The Gibbs energy change for this reaction, where silver chloride reaches an equilibrium with its dissociated ions, silver and chloride, can be calculated as follows. The Gibbs energy change for this reaction we should expect to be what? Good, positive, because this reaction we know has an equilibrium constant less than 1. This equilibrium is defined by a KSP, a solubility product equilibrium constant. And we know that because silver chloride is only sparingly soluble, the KSP for silver chloride is less than 1. Therefore, this reaction should not be spontaneous in the forward direction at equilibrium. So, if we calculate the standard Gibbs energy of reaction from our Gibbs energies of formation of each of our products and reactants, it'll look like this. Our first product, silver cation, of which we only have quantity 1 mole, and standard Gibbs energy of formation of positive 77.1 kilojoules per mole, plus 1 for chloride times its standard Gibbs energy of formation, negative 131.2, all subtract 1 times the standard Gibbs energy of formation of silver chloride, negative 109.8 kilojoules per mole, gives us an overall Gibbs energy of reaction equal to 55.7 kilojoules per mole. Sure enough, this value is positive, like we would expect for a reaction that's not spontaneous in the forward direction. And we can calculate the solubility product equilibrium constant, the KSP, for this reaction, given that we know that delta G for a reaction under standard conditions is equal to negative RT times the ln of K. We now have a standard Gibbs energy of reaction, positive 55.7 kilojoules per mole. That's equal to negative R, 8.3145 times 10 to the minus 3 kilojoules per mole Kelvin at 298 K times the natural log of our equilibrium constant, which in this case is KSP, our solubility product equilibrium constant. To solve this equation, we'll divide both sides by this whole quantity and then raise both sides e power. So our KSP ultimately becomes equal to e to the negative 55.7 divided by ideal gas constant times temperature. Put all of that denominator stuff in parentheses, and we get a KSP value of 1.73 times 10 to the minus 10. This is very close to the tabulated value for KSP of silver chloride of 1.8 times 10 to the minus 10 under these conditions. So our thermodynamic calculations have verified our experimental ones. And we can tie now the ideas and concepts of thermodynamics and spontaneity to our discussion of equilibrium.